Hello, math humans. We're going to do 4.1 today. We're going to be talking about antiderivatives. Our objectives are that we're going to start the discussions on antiderivatives, and then we're going to manage some basic integration techniques. And then we're going to start calculations of the area under a curve. Guess I had a brain fart and didn't fill out the rest of your objectives. That's kind of funny. So if we talk about notation first, okay, we know that capital F is an antiderivative, okay? Little f is a function, okay? All right, so then if I have the integral of f of x dx, so remember this is called an indefinite integral. You have a little mood music playing in the background. So when you have an integral, it is important that you have your function, and it is important that you have your dx. It's also important that your variables match, and it's important if you have multiple things in your function that everything is in parentheses so that we know that the dx applies to everything inside the parentheses. Okay? If you are doing an indefinite integral, when you are done, you're going to get some values and you get plus c. Because remember that the c is talking about creating a family of values that are moving up and down the y-axis, because that's what technically your plus c is. All right. The other way that you're going to see an integral is a definite integral. So this is called a definite integral. And it would be definite because it goes from A to B, and so it has a specific beginning point and a specific ending point. Okay? So I just have a lot of things to tell you in general about integrals. So integration is the inverse of differentiation. Okay, so it is the inverse of differentiation. Okay, if I have f of x dx, let me scoot my paper up so you can see, is equal to f of x, notice it's a capital F, plus c, just some vocabulary. This is your antiderivative. This is called the constant of integration, and we talked above about what that constant of integration does. And this is called your integrand. And then if I had a and b, those would be your integrand limits. Okay, alrighty. An interesting fact is if I take the derivative of a function, of an integral, I get back to the original integral. So if I take the derivative, and then this will lead us to the second fundamental theorem of calculus. And we'll talk about that in some sections that are coming soon. But when we're taking a derivative of an integral, that's going to lead us to the second fundamental theorem of calculus. Here are your basic integration rules. And there are just a few of them. So the integral of 0 dx is going to equal a constant. The integral of k dx is going to equal kx plus c. The integral of k f of x dx is the same thing as pulling the constant out front and then integrating. Okay? Remember that we like to make our math as simple as possible, so that's why we want to take that constant out front. The integral of f of x plus g of x dx can split it into individual components is f of x dx, and then the integral of g of x dx. The integral of x to the n dx is going to equal x to the n plus 1 divided by n plus 1 plus c. Remembering that integrals go up in power. The integral, I think I'm going to run out of room, so I'm going to scoot them over a little bit, of the sine of x is a, except I forgot my dx, is a negative cosine of x plus c. The integral of the cosine of x dx is the sine of x plus c. The integral of cosecant squared x dx, you can't see that, is a negative cotangent x plus c. Come back up here to the top. The integral of secant squared x dx is going to equal the tangent of x plus c. The integral of the secant of x tangent of x dx is the secant of x plus c. And then the last one is the integral of cosecant x cotangent x dx is equal to a negative, forgot the c, cosecant x plus c. So those are your basic integration rules, okay? All right, so let's do a couple of examples. So example number 1, I'm going to have the integral of x plus 1 over the square root of x dx. Remember that for integration, I don't have a product rule and I don't have a quotient rule. So for right now, I'm going to manage this and split it into two different functions. So this is going to be the integral of x to the 2 over 2 divided by x to the 1/2. I'm going to put my big parentheses plus the square root of, actually I'm going to call it x to the negative 1/2, and then I have my dx. So technically I could split it up. I'm going to simplify first. So this is the integral of x to the 1/2 plus x to the negative 1/2, and then dx. Remember that integrals go up a power, so this is going to be, brain fart, x to the 3/2 divided by 3/2 plus a 1/2 plus 2 over 2 is going to be x to the positive 1/2 divided by 1/2, and then plus c. I tend to clean this up, and I would do 2/3 x to the 3/2 plus 2 square root of x plus c, and I would say the integral of f of x dx is equal to 2/3 x to the 3/2 plus 2 square root of x plus c. Alrighty, remember that it's important to report all of your answers well. The next example that I'm going to do is a trig example, so only a couple of examples since you guys have already been through integration once. So this is the sine of x over cosine squared of x dx. Remember there's no quotient rule, so I'm going to split this up, and I'm going to write it as the integral of the sine of x over the cosine of x times 1 over the cosine of x dx, and then this is the integral of the tangent of x secant of x dx, and that's easy because this is just one of our integration rules, so this is just going to be the secant of x plus c. So the integral of f of x dx is equal to the secant of x plus c, okay? Alrighty, so we've talked about that the c gives you that constant of integration, which is giving you a family of integrals. Alrighty, so we call that a general solution. So remember when we are doing integrals, I'll change colors. So when we're integrating, I can have a general solution, which means that if I do the integral of f of x dx, right, then I'm going to get my solution plus c, okay, and that means that those are those vertical translations giving you that family of values. I can also do a particular solution, so if I integrate from f of x dx and get the solution plus c, that means then that I have to solve for c, and that means that you have to typically be given a point that you can substitute in so that you can solve for C. Alrighty? So if we do an example of that particular problem, okay, so I think this is example number 3. So if I had capital F of x is equal to x cubed minus x plus c, and I'm given an initial condition of this. So I've already done the integration. I've gotten my constant of integration, and this is the initial condition. Well, then I can substitute this into here to find the particular solution. So when I substitute it in, I get that 4 is equal to 2 cubed minus 2 plus c, and when I solve for c, I get it's a negative 2. And then for reporting my particular solution would be f of x is equal to x cubed minus x minus 2, okay? So just as a reminder, so we don't forget the details, if I have s of t, this is equal to position, or some function that would be position. The derivative of position is velocity, and that would be v of t. The second derivative of position is going to be acceleration, which would be a of t. Well, then if I go backwards and I integrate acceleration, then I'm going to get velocity. And if I integrate velocity, then I would get position. Okay, so those are just things that we want to think about and remember. Alrighty, that is it for today. I will see you soon.